Hello. Hello, I am audible?
Audible, sir.
Yeah. Okay, we'll see. Fourth unit we already started in the previous class. Then there is a protection, all these things we will discuss. And then DC reactor are also called as smoothing reactor, overcurrent protection, and these circuit breakers. So all these things we'll discuss today. Normally, you can see that protection of AC systems is divided into two principal categories. So that is similar to AC protection and DC protection, some aspects, but others will differ. Other aspects. So there is AC protection. We have the over voltage protection, accomplished by means of a overhead shield wire, and then protective gaps and lightning arresters. These are the related to the over voltage protection. And over current protection accomplished by fuses, circuit breakers, protective relays, and then current limiting reactors. So these are related to the AC systems. Whatever I mentioned, that is a over voltage protection and over current protection. So these are the some of the protections are there. And now, in case of HVDC systems, there is some of the categories. We divide into four categories. One is a over voltage protection, accomplished similar to that of AC systems, with some differences are there. Over voltage protection is more or less AC system protection only, with slight differences. And over current protection accomplished by control of the valves. This over current protection is accomplished by control of valves, whereas over voltage protection is similar to that of the AC system protection only. Third one is a damper circuit, so that is RC circuit you can use it, and then that is to discharging control all this thing. And fourth one is a DC reactor. So there is a major advantage in the case of DC reactors and all. Are also called as a smoothing inductor, or you can say that. That will be placed before the DC filter and all. We will use this. That is what DC reactors and some of the advantages and functioning, all these things we'll discuss. And except as to over voltage protection of the DC system is entirely different from the AC system. So as I already mentioned, no, it is over voltage protection is similar to that of AC system, but others are entirely different in the comparison of AC and DC system protection. Now we'll see that DC reactors. These reactors are having an inductance of 0.4 to 1 Henry. It is connected in series with each pole of the converter station. So this value is very interesting. It is a high inductance. 0.4 to 1 Henry means that it is very high inductance. Normally millihenry and all we may be used in the inductor values, but here is a 0.4 to up to 1 Henry. There is a, suppose if I call it as a rectifier or something, this one, and in this we'll use like this as a inductor. So there is a large inductor we'll use. So all the things are once if we use as an inductor, that will be minimize the some of the ripple, all these things, many quantities we can smoothen, and sometimes we'll overcurrent, and some of the thing is we can ripple magnitude we can minimize. So all these things will happen. There are several following purposes we'll use as a smoothing inductor. You can see first one, to prevent consequent commutation failures in the inverter. Sometimes there is a chance of getting double commutation failures also going to happen. That, as I think in the previous class I explained, there is a double commutation. There is upper side as well as the lower side. Both, positive group as well as the negative group devices. Consequently, it may be happened in the commutation failures. So suppose 1 3 and then 4 6 or maybe 2 4, while it is transferring the current from one wall to other one, there is a commutation failure may happen. So in that scenario, there is a chance of getting the commutation failure, double commutation failure also. So once if we use this reactor, there is a consequence commutation failure. So not only in the double commutation failure in upper group device and lower one full cycle, it may not be happened in more times of commutation failure that we have to prevent. So by make use of an inductor, we can prevent that one by limiting the rate of rise of direct current. So that is a di by dt during commutation in one bridge when the direct voltage in the other bridge is collapsed. So this is one of the major function we can use it. Once if we use this inductor, it will prevent the failure, commutation failures, and also to limit the di by dt in the DC side. So this is the one function. Another one is, second one is to decrease the incidence of commutation failure in the inverter during dips in the alternating voltage. So this also we can see that in the inverter station, so means there is a rectifier station in this side. After the rectifier station, we'll use there is a reactor, and then of course let it be as a what you call it as a inverter station in this side, and this inverter station we use as a AC supply in the what you call it as input, and this output side is a DC will be there across the inverter. So now the problem is once the voltage is in the dip, that means this voltage is very lower side in the AC voltage, there is a commutation failure in the inverter. So when if it happens as a voltage dip in the inverter side, then the commutation failure is going to take place. To decrease that incidence of commutation failure, if we use as a reactor. And third one, to decrease the harmonic voltages and currents in the DC line. After rectification station, generally we call it as a DC line. So there is a input is AC supply, and then we are using as a rectifier station. After that, as a reactor, all these things, protection thing will be there, and then that line after that it is transmitted as a DC, and it is connected to as inverter station to bring back to that of again AC form. So in that case, the harmonic voltages and currents in the DC line, it will decreases the voltage as well as the current in the DC line, that is harmonic voltage as well as the harmonic current. So anyhow, after this there is one topic is there, harmonics and filters. There we will discuss elaborately what is the characteristic harmonic and non-characteristic harmonic, as well as how the filters also there, how to minimize that harmonic by make use of a filter. There is a different types of filters that we can say that single tune filter and double tune filters. All these things will come across in the after this only, because that is also there in our syllabus. Different types of filters we need to discuss, but that filter design you can refer if you want more elaboration also. We can have a lot of research papers. So I will explain one of the research paper derivation design also, if possible, because there is that is not in syllabus, but just for understanding how we can able to implement all this single tune filter and double tune filter also there. So these are all just we are using as a RLC is connected in series. Then what will the resonance frequency, all these things. And double tune filter, what we will do is RLC in series, and then parallel combination of some of the L and C in series with the RLC, like a second order high pass filter, and like that we have many number of types of filters that also we are going to discuss in the this unit only after this topic. Now, these all about decreasing the harmonic voltage and currents in the DC filter. Another one is to smooth the ripple in the direct current sufficiently to prevent the current from becoming as a discontinuous. This also an important or almost at light loads. Under light load, what will happen? There is a chance of discontinuity current. Now what will happen? The smoothing reactor, or also called as a DC reactor, ripple in the direct current sufficiently to prevent the current from becoming as a discontinuous. So that means it will avoid the discontinuity, or you can say that sudden changes it won't allow. No, that will maintain constant current in that case. So it will avoid some extent becoming as a discontinuity under light load conditions. So that one is the fourth one. Fifth one is to limit the current in the bypass valves due to the discharge of the shunt capacitances of a DC line. So the bypass valves are one pole or fired simultaneously. In the previous class, I think same we discussed as a bypass valve. Whenever if any of valve is failed, so we make use of the bypass valve, and then current in the bypass valves also you have to minimize some extent. Discharging of the shunt capacitance, because the transmission line there is a shunt capacitance also will be there the DC line. These all about some of the functioning. Another one is to limit the crest current. So crest current is nothing but a maximum or a peak current. Crest current in the rectifier due to short circuit in a DC line. So whenever the DC line is short circuited, generally it will happen rarely, because a lot of protection is there in the DC transmission also. If it will happen, suppose the limiting of the crest current. So once the short circuit is happened, there is a lot of high current will generate. So that has to be minimized. It is a peak, or you can say that with less time it will generate as a very high current. So to minimize that, we can use as a crest current. And the inductance of such a reactor is usually determined from the consideration of 1 and 4. So the value of inductance we have to determine, or you have to decide based on the 1 and 4. So what is the point 1? You can see that to prevent the commutation failure and as well as smooth the ripple. So these are the 2 points majorly we have to consider while we are selecting the value of the reactor. So one is commutation failure. This is the major problem in generally. Consequent commutation failures may happen, and another one is finally our intention is to reduce the ripple content in the current waveform. So these are the two major factors to minimize you can say that commutation failure as well as the ripple. That is the reason we selected what you call it as value of the reactor. So that will be based on the point 1 and fourth one. There is a inductance should be chosen prevent the resonance in a DC circuit at the power frequency. In general, we will consider only the commutation failure, consequent commutation failure, and smoothing the reactor. So that is a ripple magnitude you can minimize. Smoothing reactor is connected before the DC filter and in series with the converter. So that's I already drawn the diagram. There is a converter here, and then reactor, then there is a DC filter, and this reactor is connected in series with the converter. So that's what. Apart from smoothing the direct current, it also solves the buffer between the converters and DC line. So anyhow, this is the major protection in the case of rectifier stations and all. So the sizing of the reactor we discussed here majorly depends on 1/4 parameters we have to consider while we are selecting the rating of the reactor. Depends the various requirements including the reduction of ripple in the current. So that is this sentence also says the fourth point is related to the reduction of the ripple content. So the major role is we have to choose what is the value of the inductance. I told no, let it be value is 0.42 1 Henry. So this is the value of inductance we need to place, but depends on our requirement, depends on our application. Based on your parameters you have to select preference, and you can select what is the value of the reactance. That's what we mentioned here. Various requirements including the reduction of the ripple in the current, all these things will influence on the size of the reactor. And DC line, in the case of bipolar system, because we have a HVDC different scenarios. So bipolar system consists of two conductors, and one operating at a positive polarity and other is operating at a negative polarity. So extra high voltage DC line bundled conductors to minimize the effect of current. So the design of DC line is carried out with similar consideration as a AC line. So the design of DC line and all it is not come under this DC reactor. So what is our intention is we have to select the size based on our minimization of the ripple and commutation failure minimization, or you can say that. And then performance of the insulations is different with DC voltage, and problems of pollution are severe compared to the AC operation, but the converter control allows reduced voltage operation under heavy polluted conditions. So the converter controls reduction of the voltage operation under heavy pollution condition. The protection against faults in a DC line is invariably brought to the converter control. So all the lines, so in the rectifier station it is going to be controlled normally. This is mainly due to the non-availability of the DC breakers in the earlier stage, but not now. In the initial stage, we have as a something circuit breakers in the AC side, but DC side circuit breakers are not developed up to the mark of the technology. But nowadays there is a lot of improvement is there in the DC circuit breakers also. Anyhow, it will come under after this slide. That is the reason normally non-availability of a DC circuit breaker. So the what you can say is rectifier station will control the HVDC system in the earlier. However, reliability of the converter control has led to its continued use even with DC breakers has been developed. So that is based on the reliability. We can extend that even after development of the DC circuit breakers. So may be required, means DC breakers may be required under a special operating requirements such as transfer from ground to metallic return and multi-terminal system operations and all. So anyhow, there is a one unit we have that is a multi-terminal system operation. You can see same. I will repeat in the consolidated manner, or you can say that the summary based on the smoothing reactor function. So whatever we discussed so far in the previous slide, that just for a brief summary I can give here. The function of smoothing reactor. They reduce the incidence of commutation failure in the inverter caused by the dips in the AC voltage at the converter bus. So that is one function. Another one is they prevent the consequent commutation failures in the inverter by reducing the rate of rise of current. That is another one. They smoothen the ripple. Just something maybe order may change, but these are the major functions. Smooth the ripple in the direct current in order to prevent the current becoming discontinuous at light loads. They decrease the harmonic voltage of the currents in the DC lines, and they limit the crest current in the rectifier due to short circuit in the DC line. Another one is they limit the current in the valves during the converter bypass wire operation. So all whatever we mentioned in the earlier, same thing. There is a some functions. If they ask the question, write a short note on DC reactor. So first we can explain all these functions, and we can little bit elaborate. And here you can see that while we are using as a frequency versus a capacitance, that is a filter capacitance, smoothening reactance, inductance and all. There is a back-to-back HVDC system. Last three functions are not relevant. For the back-to-back HVDC system, the system with the DC transmission lines, the inductor values from 0.27 to 1.25 Henry are being used. Again, there is a large reactor because if any short circuit is happened, if large inductor is there in series with the line, that can prevent the short circuit. So that's what we noticed in case of one of the power electronics topic also. One thing is voltage source inverter and current source inverter. There I can say that one single sentence, reliability of a current source inverter is more when comparatively voltage source inverter. So why that sentence made there? In case of voltage source inverter, if any commutation failure takes place, that is in the leg 1, leg 2 or leg 3, that means 1 and 4 and then 3 and 6 and then 5 and 2. So if any devices are conducting at the same time due to commutation failure, then automatically in VSI, voltage source inverter, input side is a less impedance or a negligible impedance. That's why there is a dead short circuit will happen. But whereas in case of current source inverter, one thing is a large inductor or reactor is connected in series with the supply. Then the impedance offered by the source is a large in case of current source inverter, but whereas in case of voltage source inverter, impedance offered by that will be less or negligible. Because of large impedance offered in a source side, if any commutation failure takes place in the inverter side, or let it be any of the devices in the same leg devices are conducting, because of the reactor, it can withstand some extent. Meanwhile, you can rectify your fault, or you can clear fault, or you can isolate the system. In that scenario, reliability will be more. So because of a reactor only. So in the back-to-back HVDC system, valve ranges from 12 millihenry to 200 millihenry. So that is only in the case of back-to-back system. And the sizing of the reactor is done not only from the consideration of mentioned above, that means we consider commutation failure as well, ripple magnitude, but also for the point of view minimizing the effect of lower order harmonics in the resonance. So here harmonics also I mentioned, there is a lower order harmonic quantity will be more when comparatively higher order harmonics. You can able to minimize that lower, and also in apart from previous considerations, you can also consider for minimization of the lower order harmonic. So necessary to avoid series resonance of the DC circuit at fundamental frequency, and especially in the second harmonic reduction. So the effect of the inductor wall on the resonance frequency, you can see that once if we plot resonance frequency is reduced by increasing the inductance. So that's what inductance if increase, resonance frequency also going to be, because this is L1 and then we are go on increasing the inductance value, automatically you can see that the frequency is going to be decreases. So now this is the actual connection how we are using as a reactor. I mentioned there is a controller and in series with that you can connect as a reactor. Inductance value must remain practically constant because we cannot change oftenly because it is a huge inductor value. Under dynamic conditions or considerations, we cannot change the value of the inductance oftenly. So that will be as a practically as a constant with variations in the direct current. Even though the current is varies because current has to pass through the reactor only because it is in series with the controller. This requires air core construction. Smoothing reactor helps to limit the fault current in a DC line, and this feasible only if the reactor does not get saturated by the fault current. But some cases, there is another reactor also there, saturable reactor. Sometimes it may be used in the, chopper case also, and what you call it as Morgan chopper. I think if you remember, in a power electronics, there is a Morgan chopper will be there. There will use as a saturable reactor. That is little bit will function as a switch only. What we'll do is immediately it won't change anything. Suppose if it is positively saturated, to bring back to negative saturation, it will take some time. Once if it is completely saturated, it is allowed to pass the current. Until that, it will remain in the open circuit mode. So that is a saturable reactor. Will there is a one more reactor is there. What they mention is here that should not be as a saturation because it will act as a functioning fashion. That's what we mentioned one statement here, that the saturable reactors used for the limiting the di by dt in a thyristor valve cannot be replaced by smoothing reactor. So if it replaced, automatically the saturation is takes place, that will be conduct and it allows the current. So all these problem will arise. The location of the smoothing reactor can be either at high voltage terminal or at the ground terminal. So you can see that this is the high voltage terminal, and also we can use as a under ground terminal. So preferably you can use both high voltage as well as the ground terminal. Then the necessary to have a smooth reactor order to 5 to 10 millihenry on the line side and protect the converter station from the consequences of lightning strokes also. Now, if lightning strokes also happened, there is a device conduction will take place. That also we can prevent using this. Advantages of having a reactor at the ground side, I mentioned this. You can use both in the high voltage side as well as the ground side. So there is a advantage also there if we connect as a ground side. What will be happen? It will allow the converter ground fault can be cleared by converter control itself. So if you use that, you can able to rectify the ground fault. So insulation level of the reactor also is reduced for this location of the reactor. If you use that insulation level also can reduce. There is a little information available on the choice of the optimal sizing of the DC reactor. Based on this formula factor, you can able to decide the size of the reactor also. There is a SI factor is there. What is SI factor is the ratio between rated direct voltage. Normally it is in the HVDC system we can use as a in kilowatts only, the direct current. There is a circuit inductance in millihenry because you have to find the factor SI. That factor is VDN by L into IDN. L is the DC circuit inductance in millihenry, and V is, we can say that direct voltage or a rated voltage in kV, and IDN, I can say that there is a direct current. So which includes the transformer leakage inductance also, that because we are using as a transformers also in the source side as well as the load side before connection of the rectifier station and after connection of the inverter station. There is a tap changing transformers will be used preferably, because to control the voltage also is required. That's why tap changing transformers will be used in the rectifier station as well as the inverter station. And the SI factor for back-to-back HVDC system, there is a variation is a 0.24 to 1.3 meters per second. So higher the factor, lower is the rate of rise of the fault current. So based on that, you can decide what is the value of inductor. So once the SI calculated, and you can able to decide that. Alternate the criteria for the sizing of the factor. There is, that is one option. There is a alternate criteria also there to sizing of the reactor. The ripple in the direct current. The based on the ripple in the direct current, there is a feeding a constant voltage source through a constant inductor, that you can see that there is a voltage source and it is connected to as an inductor. The peak value of the ripple is given by, there is a lot of equations are there based on the value of what poles we are using, all these things. There is a peak current, you can see that no load DC voltage of a converter, that is a VD naught, and there is some empirical relations is mentioned. The number of converters connected in series, you may get doubt here why number of converters connected in series, because this HVDC transmission may not be used directly as a what you call it as 6 pulse converter. So the number of converters you can use connected in series to form as a 12 pulse converter, and also sometimes the walls also connected, group of walls is connected in series and parallel operation in the group of walls. So that will become to increase voltage level as well as the the current value, you can increase that. So that's based on that. And then you can see that equation, leakage reactance of the converter transformer are neglected. So previously we added that, even if we can neglect that. Major assumption in that equation is that delay angle alpha exceeds the alpha dash. There is a one more equation will develop, that is alpha dash is equal to tan inverse of pi by p by pi minus cos of pi by p. There is some empirical relation. If converter is 6 pulse converter, then this alpha dash is 10 degrees, and if converter is 12 pulse converter, alpha dash is 5 degrees. With that, peak current also varies based on your converter number of pulses. If the pulses are 12, then peak current in the DC side will be calculated using this expression, and for at maximum at alpha is equal to 0, that will be as a maximum current. Peak current expression will be like this, and then the constant K will vary for 6 pulse converter as well as a 12 pulse converter according to the above expression. So it is necessary to avoid discontinuous conduction. So that also one of the function in our reactor. We need to avoid the discontinuity conduction current in the converter wall during the system operation, and this is because of the possibility of over voltage across the walls that are transmitted from the line side. And another factor that could affect the sizing of smoothing reactor is a peak direct current during bypass phase operation caused by commutation failure. So these are the considerations we need to use while we are selecting as a reactor value. So that you can see that in the diagram, what will happen is that reduction in the surge current is not commensurate with the increase in the LD beyond the certain point. So you can see that the peak current value is going to decreases by increasing the LD current. So after that, some point of time it is become as a little bit is in the constant in nature. That's all about DC circuit, what you call it as DC reactor. Now we'll see that DC circuit breakers also. In a DC circuit breaker, there is a the problem with the DC is everybody knows that current will not go to the natural zero. But whereas in the AC side, even if you use the circuit breaker, the very instant current goes to the natural zero. It is quite simple to what you call it as quench that arc, and we can able to switch isolate the system. But whereas here in a DC circuit breaker, the current will never goes to the natural zero. So what we have to do is we need to make that current to zero artificially, and at that instant we can able to turn off that. Then that we'll see that that DC breakers which is used for the interruption of high voltage direct current is known as a HVDC circuit breaker. Interruption of the high voltage direct, that is what HVDC current is known as a HVDC circuit breaker. So our intention is to break that connection that is in the DC only. Then there is available HVDC breakers are nearly 33 kV voltage rating and 2 kilo amperes are the current rating. The main problem of the HVDC circuit breaker is that DC is unidirectional and hence no 0 point in the DC system. So this is the major problem actually in HVDC system, as I mentioned just before. The current is never goes to the zero. Whereas in the AC case, very positive and negative cycle, current reaches to the natural zero. Automatically, you can able to quench that arc at that instant. But whereas here, that is the main problem is zero current will not happen in a DC system. The fault current in HVDC circuit breaker should be reduced to the zero by use of some external methods. So that current you have to bring it to zero, whatever mechanism we can use it externally, we can reduce that current to the zero. Arc quenching medium of the air brake circuit breaker is either oil or a air blast, you can use it. This HVDC circuit breaker is a switching device that interrupts the flow of abnormal DC current. So what it has to do is it has to interrupt that abnormal DC current in the system. When the fault occurs in a system, the mechanical contacts of the circuit breaker are pulled apart from the circuit is open. So if any fault is occurred, the circuit breaker has to be operated, or mechanical contact of the circuit breaker has to be pulled or separated. So that will give in this circuit breaker has to be open. The HVDC circuit breakers difficult because the current flow through the unidirectional and no zero current. So these are the another reason you can see that current is as I said now, when you are using as a what you call it as thyristor, current is always flows as a unidirectional current only. But the problem is in this case current bring it to the zero is a difficult task. The main application of this circuit breaker is to interrupt the high voltage direct current from the network. So if any fault is occurred, it has to interrupt from, or you can say that isolate the system in the DC network. AC circuit breaker easily interrupts arc at natural current 0 and AC wave, but whereas zero current in the interrupt at also 0. So that means at 0 current, energy to the interrupted is also be 0. Once the current is 0, automatically energy also is become as 0, because any one of the parameter fact that one voltage or a current is 0, power is 0, and energy also 0. The contact gap has to recover the dielectric strength to withstand the natural transient recover voltage. With DC circuit breakers, the problem is more complex, as the DC wave does not have natural current 0. So that is only we are telling repeatedly. There is a current never goes to the natural 0 in that aspect. So forced arc interruption would produce the high transient recovery voltage and restrike without arc interruption and ultimate destruction of the breaker contact. So that is also the problem. Design of HVDC circuit breakers, there are three main problems to be overcome. This, while you are designing as HVDC, what is the main problem is creation of artificial current 0. So I mentioned no, normal DC will never go to the natural 0. So you make use of the external circuit such a way that that current you have to bring it to the 0 level. So creation of a artificial current 0 point you have to create. Prevention of the restrikes arc and dissipation of the stored energy. And this artificial current 0 principle are used in HVDC circuit breakers for arc extension. So our intention is same again, current has to bring to 0 and we have to quench that arc, and finally the current is minimum. To quench that arc, we can make use of the current at the 0 conditions. By introducing as a parallel LC circuit, how it has to be generated as a artificial current is 0 instant. For that we use a LC circuit. The current is adjusted to the oscillations. So in a LC circuit is used, you can make that current is in the oscillation. So once while it is oscillating current from maximum to minimum and then decreases to the 0, again it will build up in the negative and reaches negative maximum, again reaches to the 0. These instants will happen. Under that any particular instant you can able to turn off your or you can say that circuit breaker has to be operated. Oscillations are served and have several artificial current 0 points will occur. There is a break extension arc at one of the artificial current 0. So with a many number of oscillations in that, there is a many points are there to get it as a 0 current. So at that instant artificial current is 0, then you can able to break the extension. The crest current of the oscillation must be greater than the direct current be interrupted. So that is also one condition. This is our operation of HVDC circuit breaker. You can see this is our main contact. So what is mentioned is here, there is a L and C are in series. Across there is a main contact, the DC circuit breaker. There is a auxiliary switch S1 will be there, and then there is a resistor R is connected in series with the S2. So this is what a very simple circuit created. L and C is connected in series and parallel with the main circuit, and S2 there is another switch and S1 is another switch connected to as a R. R is our resistor point. Under normal operating condition, what will happen? This main M or you can say that there is a contactor, or you can say that charging constant S2. So that means while it is charging that capacitor and all, initially we need to charge only, but the main contact M also will be under operating condition. What will happen? S2 remains closed, so that means this one will be closed. Once if this is closed, what will happen? Anybody? This is going to be charged through this path. So now we can see this is going to be charged. Capacitor is charged to the voltage through the high resistance R, and then because this is also on no initially, then there is directly is going to charge through the source. So this is the way it is going to be charge R, S2, L and C and so on. So contact S1 is open and has a line voltage across it. If this is open, already S2 is closed, then only the capacitor is going to charge through this path. So that's what you can able to get it. So capacitor is C is going to charge, and S2 is on condition, but S1 is open. Initially, this S1 is going to be open. Once it is open, if this portion is short across this point and this upper plate is connected to the positive and lower plate is directly connected to the negative, and hence we can say that capacitor is open circuit, the voltage across that will be as a source voltage. This indicates discharge of the capacitor C through inductor L. That means this discharging through inductor L, main contact. This one is a main contact, and the auxiliary contact is a S1 up to an oscillatory current. So once if it is happening, there is oscillating current is going to be takes place. Now we can see that oscillating current waveform in the second one, continuously it is going to be oscillate in this fashion. So at this point you can able to interrupt, or this point or this point. So wherever is needed, you can able to decide that interruption point. So this, if you notice this, artificial current is 0 are created at the circuit breaker main contact M. This is our main contact M, is operated at a current 0. After that, the S1 is open. So once it is current is 0, then the walls are not conducting or anything. So then what will happen? S1 is going to be open for contact S2 is closed. So once that is artificial current created 0 and the circuit breaker main contact M is open. Once if it is open, then there no meaning of closing the S2. So you can able to open that, and S2 is going to be closed. Now that means cycle is going to be repeated. So another, that is one way. Another way of interrupting the main direct current by diversion to the capacitor, there is a one you can use, there is a resistor also you can connect. So diversion of capacitor, so that magnitude of the current to be interrupted by the circuit breaker becomes smaller. So magnitude you can become smaller. This shown in, I will show the diagram here. By you can able to minimize that dV by dt also using that. The problem of prevention of restrikes is very intense in oscillating current DC circuit breaker, where the time in which the current is chopped is very small. So while you are using this scenario, chopping current is minimum, or you can say time taken to chop that current, or the operation is going to be very small. That steps surge of the restriking voltage across the breaker terminals is produced at the circuit breaker must be capable of withstanding that voltage. So if that voltage is unable to withstand that breaker, automatically again there is a circuit breaker is going to be failed. So there is a high rating of withstanding capacity of the voltage you can make use of. That is about DC circuit breaker. Now we can move on to the protection against overcurrent. You can see that in the there is a two protections I mentioned. One is a overcurrent protection, another one is a over voltage protection. So that is the left, and then we'll move on to harmonic as well as the filter. So these are the topics you need to cover in our fourth unit. There is a protection against the over voltage. They mention only the over voltage, but anyhow there is a small topic in the over current also. That is the reason I am mentioning as a over current as well. So the protection against over currents, you can see that over current protection is converters is based on the principles like those used in the AC systems principle only, while your factors that must be considered in depending on a protection system, one is a selectivity, sensitivity, reliability and backup. So these are the four factors must consider. The main feature of converter protection is that it is possible to clear the fault by fast control action. So that is not only in HVDC, in any AC systems also, in a power system aspect in general, there is a lot of sensitivity parameters are there, like frequency and all. Frequency deviation, it is allowable only 3%, or maximum extent a little bit 4 to 5%, but it is all about very sensitive parameters. You have to clear that fault as much as possible or with less time. It is not in the seconds, it is all about the milliseconds and microseconds of time we need to monitor. That's what now all the data analytics what we are doing in the power system case also, within a second of time, the lot of iterations, or you can say that many number of data points we are collecting within a second of time. So based on the data points, we can analyze how the system performance. We cannot wait until 1 minute or 2 minutes to recover all these things. So that is the reason we mentioned here. There is a protection in that possibility. Clear that fault is very faster action, that is less than 20 milliseconds by blocking gate pulse or a current regulator and control. So even though if you block the gate pulse, but once if your devices are on condition, the converter is in the on state, so what will happen? Automatically some more time the devices are going to conduct due to the inductive load, or until unless if you bring that current to the zero instant. So all these things will happen, it is going to conduct. So that's why we need to bring back to that of original state or recover the fault with 10 milliseconds of time. The selectivity is also enhanced by high impedance of the smoothing reactor and the converter transformer. That's what in the first topic we covered today. There is a DC reactor. So that is also the large impedance we calculated. For that there is a different scenarios, different functioning considerations we have to consider to select as the size of the reactor, all these things. So to enhance that selectivity, we can use that the impedance of the smoothing reactor must be as a high. And further, converter are divided into independent valve groups, such that production system must be able to switch off only in the affected valve groups, not on total bridge, or you can say that in that bridge area, the affected valves are, there is a grouping that, that's what you can see that normal in HVDC system, as I mentioned repeatedly, it is not a 6 pulse converter, it will be as a 12 pulse converter, two 6 pulse converters connected in series, and there is a poles. Now the protection system, we can notice here there is a overcurrent protection, then valve group protection, and then pole differential protection, and this side is a circuit breaker and smoothing reactor. So all lot of protection equipment is there. They consider that, as I mentioned, as a 12 pulse converter, these are the protection systems are used. This does not show protection against DC line fault, but there is a under voltage or a transformer protection also there. The basic protection against converter fault is provided by the wall group differential protection. So that is what one of the protection scheme, which compares the rectified current on the wall side of converter transformer to the DC current measured on the line side, so of the smoothing reactor. So these two will compare. Consequently, the differential protection is employed because of its selectivity and fast detection. So if you use as a differential protection, there is a fast detection. Overcurrent protection circuit used as a backup, and then level of overcurrent required to trip must be set higher than that of the valve group, and differential protection is to avoid tripping which fault outside the station. And the pole differential part, because these are all individual protection scheme are used in the HVDC system, what that each one is going to be function. The pole differential protection is used to detect the ground fault which may not be otherwise detected. So such faults at the neutral bus and the fault clearing action of the protection circuit is to be blocked. The valves and at the same time trip AC breakers of the affected group of the valve. So if any valve is affected, so that group is going to be tripped because of we are using as a protection system. Fast tripping sequence is used for the interruption of internal fault where there is a danger of valve damage is going to be take place. So this involves forced retard. That is also you can say that increasing the delay angle of the rectifier is about 150 and so on. So combined with the signal to trip the AC circuit breaker. Then you can see that there is a pulses are blocked after 20 milliseconds. This allows the inverter action at the rectifier station to try to reduce the current before the converter is going to be blocked. So now the faults producing overcurrent are classified into three categories. That is the internal faults which cause high overcurrents but are very infrequent. So that means that will occur very rarely. Thyristor surge current rating must be chosen withstand these overcurrents. Another one is a line fault that range of 2 to 3. You can say that overcurrent in the range. If this fault is occurred, the line faults which cause overcurrents, the range of 2 to 3 per unit. These limited by the current control. And third one is a commutation failure at the inverter. So by the quite frequent, this commutation failure will happen in the regularly. However, the overcurrents are small and limited by the current controller because of continuous conduction during the commutation failure. Current reference must be reduced. So when the current reference reduces, automatically the desired current is that one, and actual current because it is all under control scheme, that is also converter current also going to be reduced. So that is in the case of one, that is what internal fault over currents very infrequent. Then normal operation may commence only after the inspection of the valve to check for the damages. In second and third one, normal operation is soon after the fault clear. So we have to check whether the valve is damaged or not in the case one, but rest of the two cases, once the fault is clear, immediately it is going to be normal operation is going to be takes place. Now we'll see in the next class over voltage in the converter station. So this is only the actual topic. Over currents and all not mentioned, but anyhow it is a sequence I'm going to explain. And all of you just give your attendance and then leave. Post your attendance in the chat box. All video classes and material I think I already shared through mail or in the LMS server also available. Each in it you just download, and textbooks unable to share, but I mailed some of you. You can share among yourself. And post your attendance